have this morning in our seminar for you Dr. Keith Henderson from the Department of Geography and Environmental Engineering. He's going to speak to you about the climate change here in the Northeast, something he's been working on for quite a while. So welcome. Thank you very much for coming. And Keith, good luck.
Yesterday I lost my voice, so we're doing charades. Okay. I thought I'd start off by showing you what last year's climate was like in Philadelphia. We had a temperature that was 1.5 degrees above average, and we were about 3% drier than usual. So I thought I'd start by asking you how that impacted you. How did you survive this year that was much warmer and drier than usual? Can you give me some specific examples of how you were affected by that? Yeah.
My air conditioning bill went up.
Your air conditioning bill went up slightly, a little bit more. I mean, this is equivalent to what climate change is telling us. We're going to be a couple degrees warmer, a few percentage precipitation higher or lower. But you can't think of too many direct examples of how that important change affected you last year. You didn't notice that it was 1.5 degrees warmer?
That was really hot.
Yeah.
You're hot anyway. My birds have a higher birds because of rain.
Okay, so we're starting to be some seasonal note. Instead of projecting it this way, what if I showed you the following graphs? Instead of looking at it just as the year as a whole, if we look at how things went monthly, the first graph is of monthly temperatures. So we start to see that the early part of the year was considerably warmer than usual. We were 3 or 4 degrees above average in the late winter and into the early spring, in which case your bill was probably a little bit lower last winter. Very hot start to the summer, which gave us a very warm early summer. But the end of the year, with the exception of September, we had a rather cool fall, and then it suddenly jumped back up again in December. The last 2 months have been very cold again. So you start to look at monthly, now maybe we can start to think of some impacts that occurred to us early in the year, later in the year. If you looked at the rainfall was actually below average many of the months until November and December, when it suddenly shot up to 40 to 50% above average in those later months, which balanced us out a little bit. For the most part, we have much drier than average, particularly late summer and into the early fall. And if you bring it down even further and look at individual events, for instance, you could look at the numbers of days over 90 degrees. We were actually right on average, which indicated maybe our summer wasn't all that unusual. If you look at the days that were below freezing during the year, we actually had about 2 weeks less of freezing temperatures in 2008 than in the normal year. Then if you have impacts that had to do with very low temperatures, minimum temperatures, now you can start to think about, well, then maybe there were some impacts, particularly for frost-free days or cooling temperatures needed for certain plants. Precipitation was actually right around average in terms of the numbers of days of rain and the amount of rain per day. So maybe rainfall-wise, we didn't see a whole lot of differences. And I go through that just to point out that when we talk about climate change a lot, we tend to talk about it in large general terms. We talk about average temperatures going up 3 degrees, precipitation becoming 10% increased or 10% below average. And those kinds of changes are really meaningless because they are so general that bringing them down to the specific impact level is very difficult to do. And so there's a whole level of climate change studies that has to do with what we call downscaling, where you can take the GCM, the global change model results, which are usually for grid cells of 2 degrees by 2 degrees latitude and longitude, or even larger. And while those models can tell us something about what's happening over North America, or maybe even what's happening over the northeastern quadrant of North America, they're not very good at telling us what's happening in specific places at specific times. We don't know what's happening with rainfall rates over southeastern Pennsylvania. We don't know what's going to happen to the number of days over 90 or the number of days below freezing. Those sorts of things have to be implied by downscaling those results, by taking the large features that the models can predict, putting them either into a smaller scale regional weather model, combining them with hydrology and vegetation and the other geographic parts of the environment to really bring it down to the level where a farmer or an energy manager or a reservoir manager could actually use those results and say something meaningful about them. And so there's a role for what geographers play there in trying to show that there's a spatial and a temporal variation to climate change that is really important, and we have to see if the climate is going to change in the future. Not only how are these averages changing, but how is variability changing, how are extreme frequency of extreme events changing, and when are those changes, and where are those changes most likely to happen. So what I want to focus on today is some research that doesn't look at future climate change, but looks at sort of the past trends. Most of what I've done is examine the past record of climate change in the Northeast United States and ask what sort of trends do we see, and how can we bring those larger trends down to some more local scale and seasonal kinds of results that are more meaningful and something that can be applied more to the impacts. So when we talk about climate change, primarily what we're looking at the heart of it are the change in the weather variables. And those variables certainly include temperature. We hear about it talked about as global warming all the time. But if the temperature were to change, the energy were to change, you would also see changes in humidity. That would affect precipitable water, which would change the rainfall rate. Pressure patterns would change, which would change circulation and storm tracks. You would get more frequent or less frequent kinds of storms in different areas. It's all elements of the weather that would shift. So at the heart of what I do is try to pick some of those variables and examine the patterns of past change and variation that we see in those variables. Now those variables change because of synoptic or circulation controls. Whether we get 10 inches of rain or 2 inches of rain is determined by the atmospheric flow that month and where the fronts were moving, where cyclogenesis occurred, how the storm tracks traveled, how much moisture was being advected into that storm. And so to really understand why climate is likely to change the way it does, you have to look at how the circulation patterns and the synoptic framework of those storm systems, etc., is changing. And then at the other end of the spectrum, we want to see how those change in variables have an impact on either society or other aspects of the environment, including the hydrosphere, the biosphere, the lithosphere, etc. So as a geographic climatologist, I'm most concerned with sort of uncovering the patterns of change in the weather variables, understanding why they happen, and then what the impacts might be. So as an example today, I'm going to concentrate mostly on the seasonality part of it. We'll look at the seasonal cycle and ask, over the course of the year, when have we seen the most change in the Northeast United States? And I'm going to focus primarily on rainfall here as the variable of choice. Then we need to look at what atmospheric circulation patterns appear to be causing that kind of change. What trends do we see in the overall environment that perhaps the circulation model may be able to predict? And then as those changes happen, how might we look at how those changes have affected, I'll look at two examples today, one in which they affect local water resources, and another example when we look at the biological effects on the foliage patterns in trees. So to begin with, let's just look at some of the seasonal patterns that we've seen over the last 100 years in terms of the climate of the Northeast United States. The two maps here show climate divisions, which the Weather Service basically breaks up each state into 6 or 8 regions that have a relatively similar climate. And the map on the left is a correlation between the amount of rainfall in that season with year. So it's basically just getting the significance of the trend. Is there an increasing trend, a decreasing trend, and what's the level of statistical significance? Anything you see in pink and red is a downward trend in rainfall or precipitation. Anything in the light or dark blues is an upward trend. So what we see in the winter season is over the last 100 years, most places have gotten somewhat wetter. They're in the blues, with the exception of the extreme northern part of New England and New York. But very few of those climate divisions are actually statistically significant. You get a little bit of a dipole. Southern New England has been getting wetter. Northern New England's been getting drier. But the changes are not very widespread. They've been fairly localized, and most have had slight trends, but they're not significant. The map on the right shows how much the rainfall has changed over that century on average. We just drew a linear line through it. In terms of inches over the century. So it has gotten 2 or 3 inches wetter in southern New England in the winter, but again, fairly localized impact. If we look at the spring, then you start to see that rainfall patterns have changed significantly more in that transition season. And all across southern New England, all across southern New York, and the majority of Pennsylvania has been experiencing an increasing rate of rainfall, or increasing amount of rainfall over the spring season. And again, it's in the order of 2 to 4 inches, which is 25% of what the average seasonal rainfall is for many of those climate divisions. So that's a fairly significant increase over a much wider zone in the spring. By summer, the trends fade out again. And in the summertime, at least over the last century, it's a fairly mixed bag of places that have increased, places that have decreased. And again, not many divisions show a very significant trend. But the biggest changes we see have happened in the fall. And if you look at rainfall alone, almost every climate division in the Northeast has experienced an increasing amount of rainfall in the autumn season over the 20th century. And again, the order of that change is anywhere from 2 to 4 inches, which is 25 to 30% of their total seasonal rainfall. So many of those stations have seen substantial increases. And so the question I had, and I wanted to look at a little bit, was why the transition seasons? Why, when we're thinking about climate change and climate trends, why hasn't summer or winter been affected nearly as much as spring and fall? What's going on in spring and fall that makes them more susceptible to change, or where you'd see initial changes there, particularly on the rainfall side of things, and what kind of impacts might that transition seasonal rain change bring about? Primarily what I'm going to show you here is the results from the fall part of the work I've done. And if we look at the fall and start to break it down by month, and look at which month those increases of rainfall occurred most in, it's not really October. October came out fairly insignificant, but September and November show a lot of individual weather stations that have had a large increase in rainfall. And there's a geographic pattern to that. Now, this isn't the greatest cartography here, but basically the squares are the stations that have experienced increases in rainfall, and the circles have decreased, and if they're filled in, that's significant. So in September, most places have increased, but the area of significant change has happened primarily out west, western Pennsylvania and New York, bordering on the Great Lakes. And most of the rest of the area has not seen too much of a change, or some stations are positive, some stations are negative. In November, almost every single station has shown a positive increase. And the statistically significant stations are scattered widely throughout. Now, it's not a great pattern. I would have rather seen the majority of those stations done that way. But you see a much more widely scattered increase in November. So when we start to think about why that change may have occurred and why precipitation may be increasing, there's an indication that there might be something different going on early in the fall that's affecting the western part of the region versus later in the fall when it's a little bit more widespread throughout the whole Northeast. Now, the reason that this map looks different from the others is that instead of using climate divisions, I went to individual stations here. Because the climate division data is only available at a monthly level. So you can only say something about monthly precipitation. When you get down to the individual station level, you now have daily or hourly rainfall available. So using these stations, you can start to ask, well, why did September increase in some areas and why did November increase in other areas? So if you start to look at some of those individual stations, here's just two examples of September rainfall for a couple of those western stations in western New York and northwestern Pennsylvania, just to show that there really is some significant trends there. You can see, particularly since the late 1950s, there's been a fairly steady rise in precipitation. You'd expect annual variation, and with rainfall it gets quite messy. But despite that variation, you do see significant trends there. Whereas early in the period, this station was averaging 2 or 3 inches a month. Toward the end, it's averaging 4 or 5 inches a month in September. Same thing with Franklin, Pennsylvania. A little bit more variation. You got one really wet year back there in the 30s or early 40s. But again, what was 2 to 4 inches has now been up in the 5 and 6 inch range later on. So those western states really have seen that increase early in the season. November, you see the same kinds of things present. Again, there's one in western New York, but another one from the East Coast in Portland, Maine, that also show significant trends upward. This one may be a little bit more of a step function than a true linear change, but significantly increasing precipitation in both those cases. Rainfall can be a result of 2 things, though. If you increase rainfall, it may be a result of more storms, but it also might be a result of heavier rains when it does rain. So what I wanted to ask was, which of those 2 is responsible for most of that increase? Is it a result of more frequent rainstorms, rain events, or heavier rains when they do come? So here are the same stations, and this is September again. And the one on the left is showing you significant trends in the number of rain days. The one on the right is showing you significant trends in the intensity of that rain when it does fall. And what seems to stand out is the same area over here in northwest Pennsylvania, western New York, that had significant increases in rainfall also have a statistically significant increase in the number of days when it's raining. Whereas the intensity of that rain is only statistically significant in a couple of places and one negative up there, which hints at least that the reason for that early season rainfall increase has much more to do with the frequency of events and something synoptic that's causing rainfall events to move through more and more often early in the fall season. A couple of graphs of the number of days when precipitation was recorded in western New York. And you can see that, again, the trends running from 5 or 10 days a month early to almost half the days towards the end of the record. And again, sort of 6 to 8 days in this case, up to 12 to 14 days later on, although you also tend to see maybe a step function in that station. So something is happening in the western part of the state that's been, at least in the last couple of decades, increasing the frequency of days of precipitation. If you look at November, the pattern doesn't show up nearly as clearly. There aren't very many stations that show an increased number of days. They're widely scattered. There are many more that show an increasing rate of intensity that are scattered around. So it's a little less clear what's going on in November. But to some extent at least, an increasing intensity of rainfall, in other words, more rain falling out when it does rain, is playing a larger role, although, again, the signal isn't all that tremendous there. But there's some hint that something might be going on more with the amount of water vapor in the atmosphere rather than with the frequency of events as they move through. And to show a couple of examples of that, trends in Portland, Maine, and in western New York, about 2100, about 0.2 inches of rain per day, up to almost 50% higher. Again, more variation certainly at the end, but some upward trend in intensities that's going on those 2 stations there. So why would rainfall increase in frequency early in the fall and increase in intensity more later in the fall? One hint as to the reason behind that comes when you look at the temperature trends during those same periods. When we go back to the divisional data here, this to show which climate divisions have shown a significantly decreasing temperature or increasing temperature over the same time periods. And you look in September, the trend has actually been toward cooling. Much of the Northeast has experienced actually cooler weather in Septembers over the century, particularly in the 70s and 80s when there was some fairly cool autumn periods. And in that same zone that showed increasing frequency of rainfall, you also see decreases in temperature. Whereas if you look later in the fall, especially in October and late October to November, most of those climate divisions are showing statistically increasing temperatures, especially along the coast and up the Hudson Valley here. You see temperatures that have been increasing every year. So again, that hints that there's a synoptic difference between what's driving change early in the transition season and later in the transition season. Something is bringing cooler, more frequent events in early in the season, but then later in the season, warmth and moisture is hanging around longer and causing warmer, larger storms later into the fall. To address that, I started to look at some of the atmospheric pressure circulation patterns that might be responsible. So what we have here are two different pressure maps. The one on the left is for 500 millibar, or roughly halfway up in the troposphere, sort of an upper air pattern. And the one on the right is for surface pressure. And what I've done is subtract a recent period, or subtracted a period back in the 40s and 50s from a period in the 80s and 90s. This pressure data doesn't go back prior to the late 1940s, so you can't look at the whole century that way. But we can look at, say, a recent 15 years versus an older 15 years, and look to see what sort of pressure pattern and circulation changes have been seen over those periods. Here's September, and if we just look at those two composites and subtract them from each other, what stands out is this area in the purples and orange, purples and blues up here, which is where upper level pressure is decreased, whereas upper level pressure is increased down over the western Atlantic. There's an indication that decreasing pressure is bringing the jet stream pattern and troughing down into the Northeast United States more frequently. And that is sending an area of lower pressure, surface low pressure, basically from Pennsylvania up through the northern New England states. Now it's a big leap here. You'd have to do a much more small-scale, specific synoptic study to do this. But if we think about the average circulation over North America, you tend to have a ridge in the western U.S., you tend to have a trough in the eastern U.S. That pulls warmer weather up in the west and brings the cool air down into the northeast. Storm systems tend to travel from a trough to a ridge. That's where you have upper level divergence, causes rising air, and so cyclones and fronts tend to travel from the trough to the ridge. So what this is suggesting is that if you have a deeper trough in September, you're going to bring cooler air down into that western region of Pennsylvania and New York, and you're going to run more frequent storm systems, more frequent fronts up along that barrier right through this area of slightly lower pressure, which may bring more frequent rain events into that area that we saw before. One reviewer of this also suggested that with this deeper trough, you might also be seeing more northwest winds coming across, and it might be linked to early lake effect events too. It's not lake effect snow, it would be lake effect rain in this case, where the warmer Great Lakes might be putting enough moisture in the air to cause some downwind precipitation events later on as well. But that overall synoptic pattern early in the fall seems to explain some of what's going on in September. A very different pattern if you look at the composites for later in the fall. If you look at what's been happening in November. In November, those negative trends have almost disappeared, or they're up over Iceland here. And instead, what you see at the upper levels is a very strong area of high pressure, much higher than usual, over the southeast United States. And that's reflected down here at the surface as well, with a very, very strong anomaly of high pressure over Bermuda. Again, if you think back to what the average circulation of this region is like, that's the area of the Bermuda High. That's a subtropical high pressure system that normally sits off the east coast of the United States. As winter approaches, that high pressure contracts, shifts southeastward, and influences our weather much less frequently as the fronts move southward and we have our winter front conditions. But in the summertime, that high expands, shifts westward, and the clockwise circulation around that high pressure system is what brings the warm, moist air into the southern United States, up into the northeast, and is responsible for our heat and humidity of July and August that we're most familiar with. And what this seems to indicate is, at least over these decades that we looked at here, that the more recent decades have had a high pressure system that held on longer into October and November. And that pressure system has not been contracting as early or as far as it has in previous years. And if that high pressure system remains locked in off the East Coast for longer periods of time, that would result in both warmer weather coming up into the Northeast, creating a longer fall temperature-wise, but also would bring more moisture in to feed into those storm systems and perhaps indicate that there would be more precipitable water in the atmosphere that might be responsible for some of that increasing intensities of the rainfall events later in the fall season as well. You can look at that in a couple of different ways. Climatologists often try to characterize circulation by something called teleconnection indices, which have to do with how some places in the atmosphere act in tandem with each other. And when you have high pressure in one area, there tends to always be low pressure in the other area, and vice versa. The most famous teleconnection is probably the Southern Oscillation Index, which is involved in ENSO or El Niño events. And as an El Niño event happens in the Pacific, pressure across the Pacific Basin shifts. Well, there's a teleconnection in the North Atlantic with one center of action down over the Bermuda High and the opposite one up in Iceland. And what's normally high pressure here and low pressure there, when one gets stronger, the other gets stronger, and one gets weaker, the other gets weaker. And that's been shown to really affect the strength of winds blowing across the Atlantic. It has a big effect on Europe's weather in terms of whether there are strong westerly winds or rather weak ones coming in. But it does have a little bit of effect on our East Coast too, because as that high strengthens, again, the advection around it brings in heat and humidity. And if you look at how that index has been affected over the last 50 years, there really seems to be a jump right after the late 1970s, when a fairly low index has become high above zero for many of the years since then, which is again some indication that there's been a climatic shift towards higher pressure in the Bermuda High region, in this case in October, but throughout the later fall season, which is again perhaps responsible for the delaying the end of fall and sort of expanding, lengthening that late fall season. That's due to some of these circulation changes that are happening out over the Atlantic Ocean. So we could look at that some other different ways, but let's sort of leave that for there. So what we've seen from the sort of synoptic end of things is that there's been an increasing trend of rainfall in the Northeastern United States. But that rainfall trend is not consistent through the seasons. It's primarily been focused on the transition seasons of spring and fall, most likely due to how early those fronts are coming in from the north and how late they're exiting, and how much moisture they're getting as they come into our region and out of our region. For the fall, it seems like the trend has been towards earlier fronts, that there's been troughing in the Northeast earlier in the year that's bringing frontal systems into the regions slightly earlier in the year, more frequently in September. Whereas later in the season, those fronts are still being fed more moisture and heat and humidity up from the Gulf of Mexico and the Western Atlantic. It's increasing the intensity of those storms as they move through. So rainfall rates climate change is much more than just rainfall is 10% higher. It's falling 10% higher for different reasons and in different ways. It's falling more frequently early in the fall. It's falling heavier later in the fall. It's falling earlier in the fall because the jet stream is troughing earlier. It's coming in with cooler weather and more frequent fronts. But it's falling more later in the fall because of the advection of moisture, and it's falling in warmer conditions with more moisture to fall out of the storm and more intense storms falling later in the year. And it's those kinds of specific changes that an impact person would be more interested in than just simply knowing what's happening to annual rainfall or what's happening to even seasonal rainfall. Because the characteristics of that rainfall may be just as important to them than how much in total is falling. So it's a good example of what you can show if you begin to try to downscale some of these results. Okay, so let me take that and apply it to two impacts that may be affected by wetter autumn periods. The first one is a little hydrologic study I did, just using some basic data from the Brandywine Creek. So the Brandywine Creek is about 30 miles west of here. It runs through most of Chester County. It's got two branches. There's a west branch that comes down basically from Coatesville, and there's an east branch that comes down through Downingtown, and then it heads out fairly close to Westchester, actually I guess to the west of Westchester, and goes down into Wilmington, Delaware, where it hits the Delaware Bay. Not a very large stream. Flows are fairly low, but it's an important recreational area. It's sort of famous historically for a number of reasons, both in terms of the Revolutionary War and also the Wyeth paintings that take place around there. But it, despite its size, does serve a wide variety of societal needs. There are 57 public water facilities along that creek, which means that local towns and communities and townships are using the water out of the Brandywine. And it serves about 300,000 people get their water out of Brandywine Creek from a variety of small reservoirs along. There are 109 industrial facilities, factories that are using water out of the creek. There are 15 wastewater plants that are putting their effluent into the creek. And there's one power plant that's responsible actually for most of the water use. On average, at least, I don't remember if this was 1990 or 2000 data, the last one I looked at, but about 900 million gallons a day of water are used out of this little creek. About 80% of that is from the power plant, which uses it to cool their towers and then put the effluent back into the creek again. So if there was any sort of increase or decrease in flow along this creek, it has the potential to impact water resources for people. It has a chance of affecting water quality of that stream and the ecology of the stream, the temperature of the water in the stream, in terms of all kinds of different users, recreational users, etc., who are using that water. So if you look at the flow, the total flow of the Brandywine, here's Brandywine flow measured at 3 different stations. The 2 at the bottom are from Downingtown and Coatesville, so they're measuring the flow up in the upper parts of the 2 branches. And then the yellow line there is from Chad's Ford, which is down pretty close to the Pennsylvania-Delaware border down here. So it's measuring the flow at the bottom. And that graph just shows you what the average annual flow of the creek looks like. Like most streams around here, there's a very high runoff in the fall due to snow melt and saturated soils. Flow decreases through the high evaporation times of the summertime, really bottoms out in September and October when the soils are dry. Whatever rain is falling is being absorbed in the soils and not running off into the local creeks and streams. And then it picks up again late in midwinter. So the best chance of flooding, for instance, on the Brandywine tends to be in the March, April, so the period we're entering now. And that does show up if you listen to the traffic reports or anyone from out there. This is an area that now floods fairly frequently and affects a lot of the commuter routes out in Chester County. Okay, this table is just a simple correlation between the flow of the river and the amount of rain that falls by month. So we've got the 3 stations, Chad's Ford, Downingtown, and Coatesville. And we've done this correlation for winter, spring, summer, and fall, just to see how closely connected is rainfall and stream flow. And you see that in the winter and the spring, the correlations are fairly high. They're 0.7, 0.8, most of them are statistical. They're all significant. So what that is telling you is that when it rains, the rivers go up. But when you start to look down to the summer and the fall, the correlations get much lower. They're down to 0.6 and 0.7. So why would the correlation in the fall be less? Why is the link between rainfall and river flow less direct in the fall than it would be in the spring?
More runoff from melted snow?
More melt, yeah, there's snow melt that's getting in there. Although that you think might actually make it worse because the snow may have fallen a month ago and then it finally runs off in March, and so it would sort of mess up your correlation.
Soil's not saturated?
Yeah, most of it has to do with the soil saturation. In spring, the soils are saturated. You walk across Mendel Field, this time of year, you're slopping through the mud. So anytime it rains, there's nowhere for that rain to go except to run off into the streams. So there's almost an immediate effect of rain and stream flow. But in the fall, if you go out across Mendel Field in the fall season, you're kicking up dust clouds because the soils have been dried out by the summer. So it may rain in the fall, but most of that rain gets soaked into the soil. It doesn't end up in the stream, so there's less of an immediate response. So we see a seasonal difference in the correlation between rain and stream flows. Now, this is basically showing the same thing. This is just for Chad's Ford. But let me just focus on this one on the left here. This is the correlation between spring river flow and spring rain. So there was, again, it was almost 0.8. If you look at spring flow with the previous winter's rain, the correlation gets worse. It's down to 0.3 or something like 3 something. But if you look at the relation between spring river flow and the previous autumn's rain, the correlation goes up again. And it actually becomes significant, 0.4 something. So what that's saying is that the water that's flowing down the Brandywine right now has most to do with how much rain we've gotten this month. It has less to do with what fell in December and January, but actually is significantly correlated with what fell last October or November. So how could this spring's river flow have anything to do with how much rain fell back in September, October, November? Christine?
The precipitation will freeze and then will melt in spring.
Could be being held somewhere as a reserve. So if it fell as snow or something that was sitting there waiting to melt off, and then when it finally melted, then it hit the stream, you'd see a higher correlation. So that's a possibility, but when you think about that, would be maybe why winter is somewhat significantly correlated. But fall precipitation probably didn't fall, and probably hasn't been held.
Because if you have more precipitation in the fall, the soils can be more saturated.
Yeah, that's what I think is going on there. The more that fall is the time when the soils are driest. So if you think about the water budget, precipitation doesn't exceed evaporation until maybe September. So from September to the end of the year, excess precipitation is recharging the soil. And the more autumn precipitation you get, the faster those soils recharge, and the more likely you are to go into the winter and spring with saturated soils. And so when the rain does come in the fall, or comes back in the winter and spring, that precipitation is not needed to recharge the soil, but instead is going to flow immediately into the river and raise river levels. So here's the same correlation, but between, this is March rain and March flow. But instead of being done for the whole 100 years or 50 years, it's done in windows. So this point is the correlation from 1912 to 1941. This is from 1917 to 1946. So that window has moved up 5 years every time. So what it's shown is that the correlation between March's rain and March's stream flow has gotten stronger over the years. So in more recent times, March's rain falling and getting into March's rivers has become a more immediate effect, that what's falling in the spring immediately raises the river levels and is more likely to cause high river flows, potential flooding problems, etc. Now, part of that may be due to what's happening the previous fall. More rain in the fall is setting the stage for more runoff in the spring. There's something else we can't disallow, we can't ignore though here. What else is going on in Chester County that would result in the same kind of pattern? Why would March's rain end up in March's rivers faster these days than it did 50 years ago? All the development that's going on out there. This area that's undergoing suburban sprawl on massive scales. And what used to be porous surfaces that absorb water is now concrete, driveways, shopping malls. And that probably has a major effect on this graph too. So without being able to do some further work, it would be hard to separate those effects. Most of what you see here may be a population development effect rather than the fall rainfall effect. But it's an example of some of the ways in which the seasonality of precipitation, when it's falling, can be linked through the water budget to the kinds of impacts we see, in both in terms of the high flow times of the year and the low flow times of the year. And if you get more rain at a key point in the hydrologic cycle, that may have impacts not only in that season, but those impacts may last into other parts of the season too, and may affect a whole variety of water resource issues. Okay, the other example I wanted to give was some stuff I've been doing much more recently. It's been looking at the fall foliage season. When I think about how we've seen significant changes in the temperature and in the rainfall in the fall, one of the things I was most interested in the Northeast was how that's affected the color season of the deciduous trees. And if you wanted to justify why that's worth looking into, first of all, there's a phenology concern. The trees go through a regular growth cycle. So you have a seasonal cycle of biology there, where you have a green up in the fall and budding of the trees and leaf out. And that kind of change signals that the trees are using much more energy, they're using water, and there's a whole change to the local energy cycle that goes on. In the fall, you have just the opposite happen. As the sunlight decreases and the trees shut off their production of chlorophyll and go into their winter hibernation. Again, local energy balances are going to be affected as those trees undergo different chemical cycles and shut down at the end of the year. A lot of people have looked at these changes in the early part of the season, in the spring. There's a lot of literature on the green up and looking at when leaf out happens. But there aren't very many data sets that look at the senescence time of the year, the fall color and leaf drop that takes place in terms of what's happening there. And is the growing season lengthening or shrinking? Is it shifting earlier or later in the year? So I wanted to look at some information that would look at that. Just from a societal perspective too, the fall foliage season has a huge economic effect. When you think about New England, upstate New York, many of those states get something like 1/3 to 1/4 of their tourists during that 2 or 3 week season for leaf peeping. Think about Vermont, New Hampshire, and some of those places. People who are coming up to visit during the time of the year and spending their money at the bed and breakfast and things to try to see the peak color season. And the way they usually schedule those is going by a set map that you see where, New York is going to peak in August or October 30th, and New Hampshire would peak in October 15th, and so they plan this stuff around that. But if that fall season were to change as temperature and rainfall changes, you'd see economic consequences in the area. Okay, so there is a data set available online for about the last 10 years that a guy up in New York has established a network of about 200 bed and breakfast and inn owners that do a twice a week estimation of how much the color's changed and what percentage of leaves have been dropped. When I first looked at it, I thought, well, bed and breakfast owners and innkeepers, they're going to say that peak season lasted from September 1st to December 1st. But it's been pretty consistent, and they really do only keep the peak season around for about a week or 10 days. So he takes those observations, averages them together, and puts out twice a week a map of the color season of where we stand today. So I've gone back over that 10 years of data and put the climate grid down over it and indicated sort of when the average timing of the season starts is, when it reaches peak, when it ends, how long it lasts. I've done the same thing with when the leaves start falling, when they've mostly fallen, calculated a raking season, how long were leaves actually falling. And this is just a couple of those maps here. This is the average start date for when the trees first start to turn color. And up in the northern areas, they'll first start to turn just before the 22nd of September. Whereas down along the coast, leaves really don't start turning until right at the end of September or even into the first week of October. The average start varies from anywhere from the 17th of September down to the 6th of October on Long Island. But just in the 10 years that I have, there's been substantial variation in when that start date occurred. That start date can vary anywhere for most places from about 5 days to about 10 days or 2 weeks. So some seasons have started about a week early, and some seasons have started about a week later. So there is some leeway to when the fall color season starts. You can do the same thing with the average peak date. When do the colors reach their maximum extent? And that ranges from mid-October in the north down to almost Halloween down in southern New Jersey. But again, that varies even larger. When you look at especially down in southern Pennsylvania, in the Hudson Valley here, there are some places where the peak season has varied almost 4 weeks in some places, at least 2 to 3 weeks from one year to the next, even just in the 10 years that we have data for. So as you go into the season, there seems to be increasing variability in how long that season lasts. And you can do the same thing for the total number of days, of color days, if you want to think of it that way. And the color season is a little bit shorter in the north. It's about a month long in the north, and it lasts about 6 weeks down in the southeast. But again, that season, the length of that season can be down here 3 weeks different from one year to the next. So some years we can have very short, less than a month. Other times we can have 6 or 7 weeks of of fall colors and leaf drop that's occurring. The leaf drop data look pretty similar to these, except they're offset by a week or 10 days. So there's quite a bit of variation. If we correlate the start date with temperatures, the day that leaf season started correlates with September temperatures significantly, but a pretty weak number. And of course doesn't correlate with temperatures in October, November, and December because peak season's already started. If you look at, the start date has already begun. If you look at the peak date, that correlates very well with September's temperatures. And even the end date and the length of the season correlate significantly too. And none of the others tend to show up very well, which is some indication in the Northeast that the early season temperatures, September's temperatures, have the most important effect, not just on when the season starts, which may be indicated more by light levels, but how long that season lasts. How long do the leaves take to reach their peak, and how long until they finally give up and fall off? And it's the early temperature that seems to sort of set the stage for that, and not so much the temperatures that are going on later in the year. I looked at the earlier temperatures too. If you go back to August, July, June, there's no impact either. So really, September was the one month that stood out pretty well. If you look at rainfall's correlations, the strongest rainfall correlations are later in the fall. They're in October and November. And of course, they're not affecting when the season started because the season's already underway by that point. But they also have a strong impact on when the peak finally occurs and how long the season lasts when it ends. So to have a good color season, or a long color season, what you would need most would be a warmer September and then wetter Octobers and Novembers that would keep the leaves from turning brown and falling off, and really extend that season in terms of its length. And just a couple maps to show that. Here's the difference between the warmest Septembers and the coldest Septembers. And it shows that the peak days do change 5 to 10 days in these orangish areas, and they change more than 10 days in the couple of reddish zones there too. So across most of the area, if you have a warm September, your fall season doesn't reach its peak for a week later than usual. Of course, it would be the opposite if you had a cold September. You'd hit your peak a week earlier out in some of these places as well. If you look at the same thing for wet Octobers and wet Novembers, especially down here in Pennsylvania and the Hudson Valley, the peak gets put off by 10 days, or in the case of us here in southeast Pennsylvania, the peak can occur as much as 2 weeks later than usual if we're having a wet October. And that can really push the fall season back almost 2 weeks into November even, when more rainfall further extends that out. So you combine the two things we've talked about, and if we ask, well, what's happening early in the season, we seem to indicate there was increased troughing, colder Septembers up along northwest Pennsylvania and the Great Lakes with increased rainfall. Well, that cool September with that increased troughing, if you believe these last few maps, would probably indicate an earlier start to the color season up in Lake Erie and Buffalo and places up in the northwestern part of the region, and it may shorten the color season up there because they didn't get the warm weather of September as we've shifted toward more troughing and cooler weather coming in earlier in the year. But if we look down to our part of the state, we look down into southern Pennsylvania, southeast Pennsylvania, New Jersey, the Hudson Valley, southern New England, we haven't felt that increased troughing yet. The cold temperatures haven't gotten to us. Instead, what we've been most affected by was that longer lasting subtropical high pressure system pumping in warm, moist air later into October and November. It's been extending the temperature of the late fall and really increasing our precipitation in the late fall. And during that time of year, that's really strung out our color season. The trees have been holding on to their leaves much longer. They've been, the color's been lasting longer, and we've really been seeing shifts of almost a week or two later into the year over 2 or 3 of the last 4 years in that situation. What we have out there right now, some people at Delaware, we put in 2 weather stations out in Chester County. One is in a field, and one is in the forest about 500 meters away. And so what I'm doing right now for a talk later is to actually see as the colors change and the leaf drop changes, what's been happening to temperature and radiation and photosynthetically active radiation at those two stations to see how much of an energy balance shift would you get if you were to change leaf season by 2 or 3 weeks. And what would that mean for the amount of moisture use in the soils, the amount of photosynthesis that might still be going on in the understory and things that would really indicate some biological changes that might be possible at the end of the fall if you see some of the seasonality of change lingering into October and November as well. So, the points I guess I'd like you to carry away from all this would be, first of all, we have climate trends. There are trends in temperature, there's trends in rain, there's trends in humidity and clouds and circulation. But never think of climate change as being uniform. Climate change happens in specific places and it happens at specific times. And not everyone is going to experience climate change in the same way. There's a geographic pattern to climate change. It's going to affect some places significantly and some places not at all. Some places are going to get warmer and some places are going to get colder. Depends on how the circulation patterns are altered by that change. It's also going to be different seasonally or temporally, and not every season is going to see the same change. And even subtle differences in how we transition from summer to winter, how fast that transition happens, when the fronts begin to come in, how long lasting does the subtropical high last, are going to create specific kinds of weather events that may alter the local climate on a weekly, monthly, or sort of extreme weather event kind of scale. And it's those kinds of events, those kinds of sub-monthly climate changes in specific places that really drive the impacts, that drive what we want to know about how rivers might react or how biomes or ecosystems might react. And so there's a real need to try to get from the large GCM climate models down to that kind of a level. And there's a lot of research that's going on these days in both on the modeling side of things and on the observational side of things to try to go from the large scale predictions down to specific times and places that might actually give applied climatologists and impact people sort of more interesting scenarios that they can then plug into water models, biological models, etc., to look to try to better gauge the sensitivity of ecosystems and hydrology to climate change and come up with some better ideas of how we might better plan for it and how the kinds of changes we might expect to see as we make that jump from the large scale to the local scale. And there's a lot of challenge in doing that, and there's a lot of really interesting work to be done there. And I made it through without charades. And when we looked at data for the Northeastern United States, and you sort of plotted that cumulative, I don't remember what we used as a cutoff, it was like 50 degrees or something, and you plotted cumulative temperatures below 50 degrees, it did something like this, and the cutoff point was about here. Well, that cutoff point was, I think, around October 1st. And if you plotted the 10 years, they did sort of, it seemed like what happened from September to October 1st held through the rest of the year. The biggest variation in accumulated degree days happened right at the end of September or the first week of October. So that's, and whether that's synoptically related to when the first cold air outbreaks begin to come down from Canada, but it seemed like there was that 4 or 5 week period where that was where the biggest seasonal differences in accumulated temperatures happened. So I think that's why the monthly temperatures were picking that up. But you're right, if you wanted to look at that in more detail, you'd have to go down to the weekly or daily scale and do some sort of accumulated degree day kind of thing there.
I'm a closet leaf peeper. That's not really fascinating. Are there measures of intensity in color? Because my subjective impression is that when you go up in Maine, you get this blast of orange and yellow in a very narrow window of time. Whereas you look at leaves in Pennsylvania and southern New Jersey, you can see one green tree that doesn't have a single orange or yellow leaf right next to one that's fully. So are there, that length?
I don't know, but I think there are. But I think most of the studies you look at are done at a one tree level, or they're done at Harvard Forest, and they're examined on an individual tree. Whereas what I was trying to do is sort of more on a landscape level. And the way that the observers do it here is basically they sort of rank it, is it 20% colored, 40% colored, 60%? So they're just sort of looking at and saying, of all the leaves in my view, how, do 20% of them showing color or 60% of them turning color? So that's how this color is ranked. So there isn't a sort of intensity of color scale on there. There may be one really bright red tree in there, but if they're all the rest are green. So this is not done at an individual species level, which because even species would differ, and even the same species in Massachusetts may react differently than one in Pennsylvania to certain temperature thresholds too, adaptation over time. So there'd be a lot more sort of localized studies, but I was here looking up at the sort of landscape level where it might have a bigger impact on tourism, and maybe not as much on the local physiology where you would have to go down to that sort of scale. But yeah, I don't know of an index. There isn't a value that's put on there. But
in the autumn, the New York Times on their weather page, they have those
they do maps like this, and I have no idea how they get those. I tried to ask, and I don't know whether those are based on averages or whether they actually have observers out there. They tend to not match up with this data set. They tend to lag behind a little bit, I think. So maybe they're a little ahead. They're hard to interpret. These ones actually look pretty similar to that. But so I'm not sure whether that's based on Weather Service observers or they never say in the little captions where that data comes from.
They don't share it.
I did get a response. I tried looking, I should look into that more to hear where that is coming from.
Because that goes back a couple decades.
Yeah.
Could you explain the Eastern Atlantic Climate Connection and how it causes the climate shift?
You have the Eastern U.S. and Europe over here. There's almost always a low pressure over the Icelandic globe, and there's seasonally this high pressure that's a Bermuda high. And that creates westerly winds that are traveling across the Atlantic. This teleconnection shows that if you pick the point in the central Atlantic and pick the point up here, that there's sort of a seesaw in pressure. When this pressure system gets higher than usual, this one tends to be lower than usual. And when the high pressure is weaker, the low pressure is weaker. And that has stayed pretty consistent over long time periods. So when this high pressure system gets stronger, this low pressure system gets stronger too, which creates a stronger gradient or pressure difference between them, which creates much stronger westerly winds. And that tends to bring mild, moist air much deeper into Europe, for example. And they get a mild winter and more precipitation coming in. Whereas when both systems are weak, you tend to get a much more meandering, meridional pattern of flow across weaker. Now, that upstream, that doesn't have too much of an effect, except that if this high were very strong and this low were very strong, you get this clockwise circulation around this high pressure system. This would be bringing warm, moist air masses from the Gulf up into our part of the country longer into the year when you have that mode of the teleconnection happening, which may be bringing sort of warm, moist conditions up onto the eastern seaboard. Whereas if you have a weak high, that is actually happening well offshore, and you expect colder air outbreaks to come in more frequently. When I lived in Louisiana, taught at LSU for a number of years, the same system in the summertime can be linked to precipitation across the Gulf South. When that high moves in, it really brings a lot of moisture into the Gulf South, and you get very wet years. When that high shrinks back, you have drought across the Gulf South too because of that moisture around the western edge of it. So there's that. There's another teleconnection. There's Alaska, northeast part of, or northwest part of Canada, and the southeast, that determines sort of how big the jet stream ridges and troughs are across North America. That one's good for the winter time. So it tells you whether you have fairly flat flow or large ridges and troughs, and has been linked to temperature in the Northeast versus the Southwest, and they're all linked together. They're influenced by El Nino in certain years too. It's a way of sort of dividing up circulation cells.
So it seems like you've seen a strengthening of this particular teleconnection. Is that what GCMs have predicted and do predict for the future?
To some extent, I mean, you rarely see the pressure predictions. You more often see rainfall and temperature, and it's a little harder to get at it's built in there, but I think a lot of times they don't want you to see it because they've tweaked with the models to get the temperature and the rainfall right, but maybe not necessarily for the right reason. There are some maps out there, and I don't think that kind of thing stands out from what I've seen as far as predictions go. I have to look back again. Most of what I've seen supporting this is from observational stuff that's been done. You can even, people have recreated this all the way back using tree rings in the Carolinas and sort of put out 1,000 years of the cycle. A couple other studies at high really have shown how in recent years it's sort of shifted over a little bit or strengthened a little bit. But yeah, it would be interesting to go now into some of the model data to see whether that's predicted to continue on. But I think that's the kind of thing that I'd be, rather than look at the temperature and the rainfall data of the models, and the rain, because the rainfall data is so bad anyway. Yeah. I'd be much more interested if the models release the circulation stuff and let you know what's happening with the ridge trough patterns and the strength of the Bermuda highs, and then you could use observational data to link those circulation patterns to more localized temperature and rainfall. That's really where the downscaling community is going. They're trying to go from let the model predict the big things that it does well, and then you extend that down to the local variables using some sort of statistical extension or something.
But you need to know why certain things are going to happen rather than just
what's going to happen. Yeah.
Mike, you mentioned your research out of Chester County to measurement stations. You said that you're measuring precipitation and then
it's temperature, wind, radiation, soil moisture, photosynthetically active radiation, which is in the wavelength that plants most often use. We only have a rainfall gauge on the one that's out in the field because you wouldn't catch much rain under the trees. So you're not going to be able to compare those two. There's humidity. The variables that show the biggest difference between the two are the radiations and temperature. Soil moisture is affected by local soil differences, so I'm not sure anything useful is going to come out of that. But as you look through last fall, we had those gauges out there. The two stations are about 2 degrees apart in temperature at the beginning of the fall, and by the end they're almost the same. And you see the same sorts of things happening with the radiation too, although it's more complicated by cloudy days and things. You don't have a nice trend down. You get sudden jumps back and forth. And if you look at it, you can see how so what I'm trying to get out the next week or so is sort of see how the differences collapse. And so when into the fall season does the difference between being in the woods and being out in the field really not make a difference anymore in terms of what's coming through it. If you held your leaves for 2 weeks longer, how much energy difference would that make?
Is there a reason or hypothesis on why the Bermuda high is sticking around longer or increasing and like the decreasing pressure? It would be most likely due to ocean temperatures. Usually when you see these teleconnection indices, like the El Nino, like the Southern Oscillation, it's linked to surface feedbacks, and it probably be linked to large-scale changes in Atlantic Ocean temperatures that are locking in higher or lower pressure over warm pools or cool pools of water. Most of them do have a cyclic effect. There's a Pacific decadal oscillation that moves around. So you do tend to see a decadal or multi-decadal cycle that goes through. So the question then is how long do we need to see before we can say these cyclical events are becoming more frequent or farther apart or less far apart. But they're linked, they're often linked to snow cover over Siberia, but especially ocean temperatures, which tend to be much more stable than land temperatures do. And so they sort of set the conditions that the circulation is responding to. Although once the circulation is established, it feeds back on itself, and what's going on in one part of the circulation in one part of the world affects what's going on halfway around the globe too. So there's sort of these large-scale precursors, and then the atmosphere reacts in different ways depending